Hi guys, welcome back. In today's lesson, we are going to be learning about our last law, which is Graham's law of effusion, and this will wrap up chapter 14. So far, we have talked about gases and how they exist in varying conditions in Boyle, Charles, Gay-Lussac, and the combined gas law. We've also considered how a particular gas is behaving in a certain set of conditions in the ideal gas law. And we've even looked at how partial pressures can total up to give us the whole pressure of a container in Dalton's law of partial pressure. And so today we're going to start by talking about the difference between diffusion and effusion. Diffusion is something you have probably heard of before. We have talked about it before. It is the gradual mixing of gases due to their spontaneous random motion. When we talked about this before, I mentioned that books often like to give this kind of an example where a person opens a perfume bottle and the smell from that perfume bottle kind of wafts or drifts around the area. You can also think of this like when you're making your coffee in the morning and that coffee smell starts to waft across the room, and suddenly, even from a couple of rooms away, you can smell the coffee brewing. That kind of movement of gas is known as diffusion. In a much more specific process, we have this kind of movement of gas, which is called effusion. So in effusion, gas molecules that were confined in a container, like a wheel, the tire of a wheel, or within a balloon, or in a soccer ball or a volleyball, where those gas molecules are able to escape their container through a small opening. So, in our experience, this is normally accompanied by a hiss sound. Like if you know that there's a small pinprick opening in a balloon or in a bike tire or in a soccer ball, and you kind of squeeze it and you can hear that like hissing sound, and you can identify the point where the gas is coming out. That's effusion. So, effusion is looking at the ability of a gas to escape a container through a small opening. So the speed that a gas can escape is dependent on how big it is. Bigger gases are going to have a tougher time getting through a small opening. The visuals that always kind of come to mind for me is actually like watching Winnie the Pooh. And there's that like kind of famous Winnie the Pooh where he gets stuck in Rabbit's house and like he eats too much honey when he's on the inside and then he tries to climb out and he gets stuck. Or if you've ever watched like 101 Dalmatians or any of those cartoons where there's like a chubbier person in the cartoon and they all go through an escape, and then the last like Rolly in 101 Dalmatians gets stuck in the exit, and like the cat's trying to get him to fit through. These are kind of visuals for what we see when we think about effusion. Bigger gases are going to effuse slower. First of all, they're going to be moving slower because of diffusion. And then secondly, they're going to have a tougher time getting through the opening. And so for two reasons, they're going to be moving much slower. Now, this sounds like a pretty simple concept, but it has a pretty strong math background. So we're going to take a second and we're going to dive into some very similar to physics, what you would see in physics, math derivations. So we start with this idea that any two gases at the same temperature will have the same amount of kinetic energy. This was something that we mentioned a long time ago. And this kind of leads us to the idea that big gases move slower. We've talked about it before when you think about pushing that cart from Costco. If you're standing still and you use just your arms, you don't like take a running jump or anything, and you just push an empty cart from Costco, and you imagine how far that goes, and then you repeat the process, but now imagine that you've loaded that cart down, you've done your whole Costco shopping, you've quarantine prepped, and now you have this big full cart and you stand still and you push that cart and it doesn't really go very far. Same amount of energy input into those two systems, but the lighter one is going to move much further and much faster than the heavier one. The same thing is true of gases. At the same temperature, smaller gases and larger gases, they have the same amount of energy. That propels smaller gases faster, and bigger gases are going to be moving much slower. The mathematical relationship for this is that kinetic energy equals 1/2 mv squared. And so we're going to take a second and we're going to look at what that means. So first of all, I want to start by looking at this equation. Kinetic energy equals 1/2 mv squared. And I want to point out a couple of important things. One is that m is still mass, just like you probably assumed that it was. M is mass, but v is something very different. It is not volume, okay? This is not a volume problem. V in this case stands for velocity, which is a physics word for speed. To get a little too specific on you, velocity is a vector, which means it has a direction where speed doesn't. So velocity is really just a representation of speed. So what we're saying is that mass is inversely proportional to velocity. So mass times velocity is going to give us our kinetic energy. So if we consider a situation where we have two different gases, gas A and gas B, those two gases at the same temperature should have the same amount of kinetic energy. This allows us then to set their two kinetic energies equal to one another. And so we end up with 1/2 mA, representing gas A, VA squared equals 1/2 MB VB squared. And so this is showing us that our mass and velocity of gas A is equal to the mass and velocity of gas B. And so what I want to do now is I want to take this equation and I want to get rid of the things that we don't need to worry about. Okay, so we don't need to worry about the 1/2 because they're on both sides. And so the 1/2 being on both sides means that that's keeping our ratio. We're not even going to worry about the squares. We're just going to look at this. And we're going to remember that this feels a lot like the other gas laws that we had. If our mass goes up, our velocity has to go down. And if our mass goes down, then velocity must be increasing. So what this whole thing says to me, without getting too involved in the math derivation, what this whole thing says to me is that lighter gases travel faster when the temperature is the same. So this is the mathematical proof for what I have been telling you, for the experiences that you have with Costco carts. Smaller things, smaller gases move faster at the exact same temperature. And this is that mathematical proof for the concept that we've been discussing. So this leads us to Graham's law of effusion. Graham's law of effusion says that there is a direct relationship between the kinetic energy of the mass and the temperature. So what we're going to do is we're going to look at how fast a particular gas moves. So Graham's law of effusion states that the rate of effusion, represented sometimes by R or V of a gas, are inversely proportional to the square root of their molar masses. Now, the square root comes from the idea that there was a square in my problem. I said it didn't really matter much, and that's true, except it does end up being a part of our derivation. We could derive Graham's law from this kinetic energy equation up here, but let's not. Okay, instead, let's just say that Graham's law tells us that the rate of effusion of a gas is equal to the inverse of their molar masses. So I'm going to switch to the board for a second and I'm going to write out the way that we are going to use this law. Okay, we are going to say that the rate of gas A compared to the rate of gas B is equal to the square root of the molar mass of B over the square root of the molar mass of A. Okay, so a few important things to point out here. The most important one is that it's inverse. So the A here moves, right? We're looking at the inverse of these, and this is the B up here. The other thing I want to indicate before we even get started is you should always call your lighter gas A. So this should always be the lighter gas. It works either way, but it will be much easier. The math will be much easier if you make the lighter gas A. Okay, it's just like a little trick to help you be good at these problems. So this is like a fairly strange law, okay? And what we need to find out is how we're even going to apply this law. So once you have this written down, oh, there's one more thing I need to remind you, and that is that you're going to need to find your lovely periodic table, okay? Because if we need molar masses, unless you have gone to the trouble of memorizing all of them, you need your periodic table for reference to be able to find the molar masses of each of these. So when we say the molar mass, we're just looking that up on the periodic table, okay? All right, so we're going to try one. We're just going to try a problem and see what it asks us. So it's asking, what is the ratio of effusion rates? Okay, the ratio of effusion rates is basically this. Okay, what's the ratio of effusion rates of hydrogen gas and krypton gas? So we are going to find, before we can do any of this, we need to find the molar mass of hydrogen and the molar mass of krypton. Now, another kind of reminder from the old things that you used to know is that hydrogen always comes as H2, right? So we're looking for the molar mass of H2. Remember the 6 in the shape of a 7? Okay, that's what this is coming from, the molar mass of H2. And then we have the molar mass of krypton, Kr. So I'm just going to go look these up on the periodic table, and I find that hydrogen H2, so 1.01, its molar mass is 2.02. That's the molar mass of hydrogen gas. And krypton's molar mass is 84.80. Remember, that's grams per mole because it's molar mass. Okay, so I'm finding that from my periodic table. Now, the lighter one is hydrogen. So I'm going to say that the rate of hydrogen compared to the rate of krypton is equal to the square root of the molar mass of krypton. Remember, I need to change their places to the square root of the molar mass of hydrogen. So this is my use moment. Okay, this is my given moment, and we could add find the rate ratio. Okay, but that's what we're trying to find. So that's my given and my find and my use. And now I'm going to go ahead and plug into this equation. So I have the rate of H2 compared to the rate of Kr is equal to the square root of 84.80 divided by the square root of 2.02. Now you can solve this out. When you go to solve it, you can either take the square root of each of these individually and then divide them, or you can divide them first and then take the square root. It doesn't make any difference. So if I did 84.80 and I took the square root of that, that would be 9.21 divided by the square root of 2.02, which is 1.42. Okay, which would be 1.42, and then I would do 9.21 divided by 1.42, and that would give me 6.49. And just to prove it, I'm going to do also 84.80 divided by 2.02. That gives me 41.09 or 41.99. Take the square root of that, and that gives me 6.48. So it doesn't really make a difference which one you do. So 6.49 is the hydrogen compared to krypton at 1. So the rate of hydrogen is 6.49 compared to the rate of krypton, which is 1. And this is why I told you to put them in that order. Or you could say the ratio of the rate would be 6.49 to 1. Okay, if that makes sense to you, writing a ratio like that, that would be H2 to krypton. And actually, this would be the best way to write your answer, would be to say that the ratio of the rate is 6.49 to 1 from hydrogen to krypton. What this means, and in the answer, is that hydrogen would be moving 6.5 times faster than krypton. And that makes sense because we said smaller things move faster, and hydrogen is much smaller. So it should be moving much faster, 6.5 times faster. So your answer should make sense rationally when you get it. If you've made a mistake in here, your answer won't make sense when you get it. So make sure you're checking your answers for things that make sense.